Welcome, everyone. Today we're doing a deep dive into some really mind-bending concepts from the universe. We're talking black holes, white holes, and wormholes.
Absolutely. And these aren't just, ideas you see in movies.
Right. They're serious concepts in physics. They really challenge how we think about, well, everything, space, time, reality itself.
Mm-hmm.
So our mission today is to kind of explore what they are, maybe how they differ, and why looking into them matters so much.
Sounds like a plan. Where should we start?
Okay, let's unpack this. Starting with the one we actually know exists, the one we observe, black holes.
The foundation, yeah.
So picture a spot in space, right, where gravity is just unbelievably strong. So strong that nothing gets out.
Not even light. That's the key.
Exactly. And they usually form when a really massive star collapses in on itself.
Crushed by its own gravity.
Yeah. And there's this boundary around it. The event horizon. Cross that line.
And there's no coming back. You're pulled in.
Gone. But what always gets me is this no-hair theorem.
Ah, yes. That one's fascinating.
It basically says, right, that this massive thing that could swallow stars, you only need three things to describe it. Its mass, its charge, and its spin. That's it.
That's the theorem, yeah. Everything else about whatever fell in its shape, its composition, all that complexity seems to be hidden from the outside.
Which sounds simple, but isn't it?
Well, what's genuinely perplexing about that is the implication. Think about it. If you, say, toss an encyclopedia full of information into a black hole, from the outside, all that specific information just seems to vanish. It's only reflected in the mass, charge, and spin increasing slightly.
Okay, I see. So the details are lost.
Apparently. And that leads us straight into one of physics' biggest headaches, the black hole information paradox.
Because information isn't supposed to just be destroyed, right? That breaks other rules.
Exactly. Fundamental laws of quantum mechanics say information should be conserved. It can't just disappear from the universe.
So that's a major puzzle.
A huge one. And that, interestingly, brings us to the idea of white holes.
The opposite number.
Pretty much, yeah. A white hole is, well, theoretical. It's imagined as the reverse of a black hole.
So instead of pulling stuff in,
It only pushes things out, constantly spitting out matter and energy. And crucially, nothing can enter a white hole from the outside.
Okay, wait. How does that work?
Mathematically, they sometimes pop up as time-reverse solutions to the equations describing black holes. Einstein's equations, specifically.
So like running the film backwards.
Kind of, yeah. And some scientists have proposed this intriguing idea. Maybe a white hole is what's left after a black hole dies or evaporates.
Oh, how would that help with the information thing?
Well, the thought is maybe the white hole then releases all that information the black hole swallowed over its lifetime.
So the information wasn't destroyed, just held and then released later.
Potentially. It offers a theoretical escape route for the information, possibly resolving that paradox.
And this is a big but, I'm guessing.
A very big but. White holes are purely theoretical. We have absolutely zero observational evidence they exist, unlike black holes, which we've seen.
Got it. Theory only for now. Okay, so black holes pull in, white holes push out. Here's where it gets really interesting for me. Wormholes.
Ah, the cosmic shortcut.
Yeah. These hypothetical tunnels, right, through space-time itself,
Yeah.
connecting maybe two super distant parts of the universe.
Or maybe even two different points in time, according to some theories.
Whoa, okay, that's wild. The analogy I always like from the sources is the paper one.
The folding paper analogy, yeah, that's a good one.
You imagine space like a sheet of paper, fold it so 2 points touch, then just poke a hole through.
Yeah.
Much shorter than going the long way around on the surface.
That's the core idea, yeah. A shortcut through space-time.
Yeah.
But there's some serious challenges.
Like what? They sound amazing.
Well, the problem is, most theoretical wormholes would be incredibly unstable. They'd likely collapse almost instantly.
So fast you couldn't even send light through.
Exactly. Far too fast for any kind of travel. To keep one open, stable enough to actually traverse,
You need something special.
you'd probably need something called exotic matter. And this isn't just rare, it's hypothetical stuff with properties unlike anything we know.
Like negative energy.
Precisely. Negative energy density or negative pressure. Something that pushes space-time apart instead of pulling it together like normal matter and energy do. We haven't found anything like it.
So another big theoretical hurdle.
A huge one.
Yeah.
And some theories even speculate that maybe a wormhole could connect a black hole entrance to a white hole exit.
A bridge between the two.
A possibility within the mathematics, yeah. But again, just like white holes, wormholes are entirely theoretical. Fascinating, but unobserved.
Okay, so let's quickly recap for everyone listening. Black holes. Observed. They suck things in, described by mass, charge, spin.
Consumers.
White holes. Theoretical opposites, spitting things out, maybe resolving the information paradox, but unseen.
Right. Emitters, in theory.
And wormholes. Also, theoretical potential space-time shortcuts, but need exotic matter to be stable, totally unobserved.
Theoretical connectors, you got it.
So we've only actually seen one of these three.
That's right. Only black holes are confirmed by observation.
So why spend so much time on the other two?
Well, if we connect this to the bigger picture, studying all three, even the purely theoretical ones like white holes and wormholes, is actually crucial.
How so?
Because exploring these ideas, pushing the boundaries of Einstein's theories and quantum mechanics, helps physicists really probe the fundamental fabric of our universe. They force us to tackle deep puzzles like that information paradox. And grappling with these extreme concepts might lead to breakthroughs in understanding gravity itself, maybe even finding a theory of quantum gravity that unites everything. It helps us understand the universe at its most bizarre extremes.
So thinking about the impossible helps us understand the possible.
In a way, yes. It stretches our models in our minds.
Okay, so wrapping up, what does this all mean for you listening right now?
I think it's about considering how exploring these, truly profound concepts, even the ones we can't see yet, pushes our understanding of reality.
It forces us to question the limits.
Exactly. What is actually possible under the laws of physics? Could understanding these things maybe one day unlock secrets to, interstellar travel or even time travel? It sounds like sci-fi, but...
The fundamental physics is being explored.
Right. So it really invites you to just ponder the ultimate secrets the cosmos holds and, the incredible unknown potential hidden in these cosmic mysteries.
There's still so much we don't know.
Definitely something to think about.